functions and the end behavior of rational functions. End behavior, remember, is what happens to the function, what happens to the y value as your x gets infinitely big or as your x gets infinitely negative. So we've been talking about functions whose end behavior can be described by a horizontal asymptote. That would have a horizontal asymptote of y equals 0, and I think you can see that. As x is getting bigger, 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 I'm approaching a y value of 0. As x is approaching negative 5, negative 10, negative 100, negative 1,000,000, I'm still approaching a y value of 0. We've also talked about functions whose end behavior is described by a slant asymptote. So I don't know exactly what the equation of this asymptote might be, but it's going to be y equals x plus something, or y equals mx plus b, right? It's going to have a slope, a y-intercept, and that is going to describe the end behavior of my function. Let's see, here's another rational function. That looks like that's being described by a horizontal asymptote of y equals 1. But not all rational functions have linear end behavior. Let's look at those. Let's look at some of these kooky-looking rational functions whose end behavior might not be described by an asymptote. Like, look at this. Show me with your bodies out there. What does this end behavior look like? I hope you're all doing this. Yes. Look, if I'm leaving the page, let's pick a different color. As x is getting big, 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 my y is getting big, but it looks like it's getting big in kind of a curvy fashion. Same thing as my x is getting more and more negative. Hey, wow, that looks like my end behavior is being described by maybe a quadratic function, or at least some polynomial with an even exponent. It could be like an x squared function or an x to the 4th function. We don't call these asymptotes anymore when they're not linear, but these are still end behavior graphs that dictate the end behavior of my function. Let's look at this creature over here. Okay, and again, there's a lot going on in the middle of a function, but the middle of the function is interesting, but it's not telling me about the end behavior. So as x is approaching something big, my y is going up, 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 and ooh, this looks kind of curvy. As my x is approaching negative infinity, oh my goodness. What type of function looks like that? Yes, a cubic, or an x to the 5th, or an x to the 3rd, or something like that, right? So this end behavior is going to be described by perhaps a cubic. This end behavior is going to be described by perhaps a quadratic. Now, I don't know their specific equations, although we'll talk about that in a little bit. But what I want to be able to do right now is to look at these functions up at the top and to be able to match them with their graphs. All right, so let's minimize this so you can take a look. And certainly pause the video if you wish, so you can really see which function is going to go with which graph. Okay. So again, when we're cutting off a little bit there, but when we're looking at end behavior, we imagine my x getting really, really big. But we came up with a shortcut, and that shortcut was looking at the controlling term in the numerator, looking at the controlling term in the denominator. So the reason we can do that is if I'm plugging in, let's say, 1,000,000, that x is what's in control. That little +5 isn't doing a whole heck of a lot. X squared in the denominator is really the controlling term if I'm plugging in a really big or a really negative x. So you can imagine, of course, this fraction line means divide. X divided by x squared, what's that going to give me loosely? Well, 1 over x. And as x approaches a really big number, a really negative number, 1 divided by a really big number is essentially 0. Same thing with 1 divided by negative 1,000,000. So I'm thinking A is going to go with this one. Hope you did too. Okay, Let's look at B. Again, when I'm looking at end behavior, I can focus on the controlling terms. X squared is the biggest degree in the numerator. X squared is the biggest degree in the denominator. When I divide those, I'm going to get about 1. That means my y is approaching 1 as my x is getting big or very negative. Hey, that's what we said this one was down here. Okay, let's look at C here. We have x to the third, who's in control in the numerator, x squared, who's in control in the denominator. So if you notice, the degree in the numerator is 1 degree bigger than the degree in the denominator. If I were to do polynomial long division, which I could for all of these, but we're just doing a shortcut, I would get y equals x plus or minus something. Wait a minute. That's going to give me a slant. Let's see, I had a slant somewhere. I'm pretty sure that's going to be this. Now again, I'm just dividing the controlling terms, but you could take the time to actually do polynomial long division and get the exact equation of the slant asymptotes. If you do polynomial long division, you'll also get horizontal asymptotes, which is kind of cool. Okay, let's look at D. I have an x to the fourth divided by an x squared. If you imagine dividing x to the fourth divided by x squared, what are you going to get? X squared. Hey, that's this puppy right here. Okay, fantastic. And E, we're imagining dividing an x to the fifth divided by x squared. X to the fifth divided by x squared, that's going to give me x to the third. So that's going to be E. Do you see how that works? So just by looking at the end behavior, you can match each function with its equation or with its graph. Now, just very quickly, if I wanted to find the actual equation of the end behavior function, I could, of course, do polynomial long division. So let's just look here. I have an x to the third function in the numerator and an x squared in the denominator. What type of function am I going to get? Sure, 1 degree bigger than on the top than the bottom, I'll get a linear function. I could figure that out using polynomial long division. Let's look at number 2 here. I have an x to the fourth. I have a degree 4 in the numerator, a degree 2 in the denominator. If I'm dividing those, I'm going to end up with quadratic end behavior. Hey, should we divide these just for fun? It's just good old-fashioned polynomial long division. I'm not in the mood to write in red. I'm in the mood to write in blue. Okay, so let's see. If I want to, I can put in some place savers here. Let's just go ahead and do that. Sometimes it's helpful when you're missing a term to put in a little 0 x to the third. It's not always necessary, but sometimes it's helpful. So I'm just going to throw in some place savers. Note that I threw in a place saver here as well. Okay, here I go. First term, x squared times what is x to the fourth? That's going to be x squared. X squared times x squared is x to the fourth. That's going to give me a 0 x to the third. You see how that's nice? X squared times 4 is plus 4x squared. And now I'm going to subtract each term. That goes away. That, well, I guess I didn't really need that. 3x squared minus 4x squared will give me a negative x squared. And you bring down the other terms. So you see that place saver there was not all that necessary. But sometimes you don't know until you get rolling. Let's start the process again. X squared times what is negative x squared? A minus 1. So negative 1 times x squared is negative x squared. Negative 1 times 0x is 0x. Again, I didn't really need that. Negative 1 times 4 is negative 4. And I'm going to subtract. That goes away, and I have a -1 remainder. But I'm done. I'm done now. So there's my end behavior. So my end behavior in this case is going to be described by this quadratic. Okay? Now you say, well, what about the remainder? You know, the remainder is why this function doesn't just look exactly like a quadratic, right? Because of that remainder, this is going to be a weird function with some crazy stuff going on around the x and y intercepts. But as the x gets big, as the x gets really negative, it's going to start taking the shape of the parabola, y equals x squared minus 1. Go ahead and graph this on your calculator and you'll see that that's true. Okay, I hope you find these as fun as I do.